Elle est jolie, une voiture. La rouge, là?
Ouais.
Je sais pas, ça.
Tu regardes. Il y a le film. Ah non, c'est parce que c'est la caméra.
Oui, c'est vrai, on est des stars, etc.
De toute façon, je pense que se concentrer sur elle. Je vais copier le son ici. À tout.
Ah non.
Ah, mais tu m'entends? Oui, c'est mieux. C'est bien qu'on voit, non?
Non, non.
Ah, mais.
On the right side, on part à la nuit, c'est participant aussi, voir si elle est bien connectée.
Oui, je l'ai activé.
Voilà. Ah oui, c'est bien.
And can you hear me?
Yes, I can hear you.
We can hear you also.
Perfect, yeah.
Fine.
Ok, en anglais au départ. Hein? Okay, so thanks to be here. We are here for the defense of Ha Nhi Ngo. I will be the president of this jury. I'm Flavien Balbo, I'm professor at Saint-Etienne, and the other members of the jury are Miss Anne Nové, who is from the Vrije University of Brussels. We have also who is the other reviewer, Mr. Wilgo Berghout, who is examiner and is from KTH, Royal Institute of Technology. And the PhD was directed by Marie-Pierre Glaise from IGRIT and Miss Elsie Kadoum from IGRIT too. And it was done with a partnership with Continental, I'm sorry, with Miss Anaïs Gourjol and Mr. Jonathan Bonnet from Continental Digital Services. So now you have 45 minutes for your presentation. After we will have a lot of questions. And so I'll let you the floor.
Yeah, thank you. So should we start now? Yes. Good morning, everyone. Thank you for being here for my defense. Today, I present my PhD topic, Continued Learning and Cooperative Prediction, based on adaptive monetization systems applied for traffic dynamic predictions. My PhD is funded by SIF contract between Continental Digital Service France and Smart Team of Computer Science of Toulouse, under the supervision of Professor Marie-Pierre Glaise and C. Kadoum, Jonathan Bonnet, and Anaïs Courson from Continental. In my thesis, we study a topic addressing the traffic congestion challenge in transportation domain. This challenge nowadays is more and more important due to the significant growth of number of vehicles. Traffic congestion challenge results in several inconveniences, including the increase of travel costs and time, negative impacts on human mental health, environmental issues, and especially the degradation of traffic safety due to collisions. In fact, traffic collision at the end of jump queue can happen frequently, especially when drivers do not have enough time to react for dangerous situations due to the quick propagation of traffic queue. So therefore, the anticipation about the existence of traffic congestion is essential to help drivers decelerate gradually before approaching to the queue. It helps reduce the appearance time of traffic congestion, avoid or mitigate the severity of traffic collision. In the automobile industry nowadays, V2X connectivity is widely used for queue warning systems. This technology allows vehicles to broadcast the queue status to the upcoming vehicles. So it helps drivers extend their visibility so to make better decisions. However, as some projects at Continental, when we deploy this technology for connected vehicles or autonomous vehicles, some limitation due to the short communication range can make the information exchanged from the leading vehicles become unreliable. So to improve the quality of traffic congestion in anticipation, we need a prediction method that can provide the accurate and updated traffic prediction for the upcoming road segments on vehicle trajectory. So to tackle this challenge, we need two elements. The first one is the updated and real-time traffic observations, and the second is a data processing method that can perform efficiently in the complex and dynamic traffic environment. Fortunately, thanks to the advance in sensor and connectivity technology, we can have the first element. In fact, traffic data nowadays are collected from diverse sources with massive volume, high speed, various types, and mostly in real time. So that allows the method based on data analytics to gain advantages in handling complexity, real-time adaptability, scalability, and data-driven insights. And so that's why now the challenge of my thesis is to tackle the second element, how to construct a traffic prediction method based on data analytics that can perform efficiently in the complex and dynamic traffic environment. In the next, I will talk about the problem formalization, study the existing methods in the state of the art, present our proposal, adaptive monetization system for driving behavior prediction. I present the evaluation of adaptive for the concrete scenario, testing scenario, and I will end up with conclusion and perspective. The traffic prediction problems we study in my thesis is placed in a road network. The figure on the left shows you an example, the road network in Toulouse from OpenStreetMap. Under the point of view of traffic prediction problems, the road network is decomposed in multiple entities from the microscopic to macroscopic. We have connected vehicle, sensor, segment, subnetwork, and network entities. To compute traffic predictions, the entities need to observe traffic data by collecting by themselves using their own sensors or interacting with other entities to exchange data. So therefore, the traffic data are continually transferred within the road network architecture via the interaction between entities. Within the interactions, there are entities who give data to the other and the entity who receive data from the other. So based on this context, the entities in the road network architecture can play two roles. When they give data and share the data, their data to the other, they are playing the role as data provider entities. And when they receive data from the other to analyze for further analysis, for example, estimating traffic dynamic on themselves, they are playing the role as processing entity. And each road segment entity can play both roles. On the example on the left, road segment entities are playing the role as processing entities. They receive data from the crossing vehicle, connected vehicles, and locally estimate the traffic prediction on themselves. For the example on the right, row segment entities play in the role of data provider entities. In fact, row segment entities having the same characteristic can be represented by a subnetwork entity, so they can gather the data and share the data to this subnetwork entity to gain the traffic insight at higher level. So from this context, the traffic prediction can be estimated at every level in the road network architecture, adapting to the need of the study. So from this context, we formulate the multi-level traffic prediction problems as follows. Given a traffic data stream sent from data provider entities, the processing entities receive the data, learn from this data, and compute the traffic predictions for future timestamps. And this definition can be given for every combination of data provider and processing entity. So we expect our solution to be generic to adapt to different testing scenario with different combination of data provider and processing entities. This problem contains some challenge. Here we determine 5 challenges: how to model the temporal dependency between traffic factors, how to study the traffic propagation in the road network, how to update model according to the trend of environment, ensure the performance of predictions for different testing scenario, and explain predictions. So that's to deal with the 5 challenges, we aim to integrate 5 components in our model: temporal, spatial, stream analysis, strong model versatility, and clear model interpretability. So from the 5 defined components, we analyze the existing method in the state of the art to deal with traffic prediction problems. Here we focus on 3 categories: time series clustering neural network-based models. They are the most well-known and common methods to deal with these problems. First, the time series-based models at the family of ARIMA models. They aim to express the prediction at the linear combination of previous observation and Gaussian noise. They can perform very efficiently in the regular traffic, and the dependency between prediction and the parameter in the model are clear to understand and explain. But their performance highly depends on the value of predefined parameter. And they require the strict assumption of data, only perform the linear modeling, and they can have the very significant error when some irregular traffic situation happen. Clustering-based models can be applied for traffic prediction problems for both spatial and temporal aspects. The temporal clustering aims to regroup the observation without having the same traffic pattern together. On the other hand, the spatial clustering aims to regroup row segments having same characteristic of traffic together to adapt the learning model for different groups. The advantages relate to no requirement about data and clear explanation about the causality between prediction and the parameter. But their performance also highly depends on the value of defined parameter. For example, changing the value of similarity threshold or the number of clusters can change the prediction accuracy. And besides, they have the rigid structure with fixed number of clusters. So it lacks the flexibility to deal with the dynamic evolution of data stream. The most common methods for traffic prediction problems recently are neural network-based model. They have strong capacity for temporal and spatial modeling, and they can obtain very high accuracy even in irregular traffic. But they express the black box nature that can prevent them from providing the clear explanation about input and output causalities. Also, they require the high computational capacity and the big data sets to train and calibrate the parameters in model. So they are not active enough to process the dynamic, the active property in the data stream. So to summarize, the table here shows you the limitations and the strength of existing methods for traffic prediction problems. It's challenging to include the 5 components we defined at the beginning in the model because none of the existing model can fulfill them. We can also observe that the stream analysis is still novel to deal with traffic prediction problems. So firstly, to address it, we explore an approach named dynamic clustering. The dynamic clustering, here we have 2 well-known methods for this approach, clustering and dense-stream. Is it the clustering-based approach? It uses the similarity between data points to determine the set of clusters. They gather the similar data points to the same cluster. And the difference between the dynamic clustering with the classical clustering is thanks to the dynamic functions such as creating, merging, splitting, removing, adjusting cluster. So this approach can continually integrate the data in the learner database and update the clustering structure of the database according to the new data points. So here, by observing the transition between clusters, we can gain the understanding about temporal dependency between different traffic dynamic clusters. And additionally, we can gain the explanation about input and output thanks to the understanding of the assignment rule in the clustering algorithm. In the other hand, our defined multi-level traffic prediction problems express the open and dynamic properties due to the different combination of data provider and processing entity, different types of data exchange, and the continued evolution of the environment. So in this case, decentralized modeling method that is capable of local learning, interactive cooperation, and continued adaptability would be an appropriate solution. An adaptive multi-agent system, or AMAS, is well known as an efficient solution to deal with such problems. AMAS propose the solution for complex problems thanks to their bottom-up design that enable the distributed learning at agent level and the cooperation between them. Agents in AMAS receive data from the external environment or the other agents, make decisions using their own skills and react. In the interaction, agents can be in 2 types of behaviors, non-cooperative or cooperative. When they are in non-cooperative behaviors, they need to be provided a set of solutions to help them overcome the disturbing solutions. And when they all are in the cooperative behaviors, the cooperation between them emerge an adequate function that can reach to the objectives of the system. So based on the principle of clustering dynamic approach and AMAS, we introduce Enregistré as a solution for traffic prediction, for multi-level traffic prediction problems. Enregistré stands for Adaptive Multi-Agent System for Driving Behavior Prediction. This is the architecture of Enregistré. Enregistré performs locally at the level of processing entity via 2 main processes, learning process and the prediction process. In the learning process, the processing entity interacts with data provider entities to detect different traffic dynamics on itself. And this process performed locally at the level of each processing entity. In the prediction process, the processing entity use the database from the learning process and cooperates with the neighboring processing entity to exchange data, to gather data, to compute cooperatively the prediction. Now I will explain all functions and processes in Enregistré from the left to the right of this architecture. For every data in the stream sent from data provider entity, Attrib firstly applies the noise filter on this data. The objective of noise filter or noise detection mechanism is to detect the traffic data containing the singular behaviors that do not correctly reflect on the traffic conditions of the road network. The singular behavior can due to different reasons. Here I list the reason according to the testing scenario and according to the characteristic of data we use. For example, in my thesis, I developed noise detection mechanism that can detect the singular behavior of drivers in free flow traffic, but I will detail it in the next session. So the accepted data point enters the Attrib, and Attrib starts the learning process to learn from this data. The learning process, to perform the learning process, we develop a new dynamic clustering algorithm based on AMAS. Processing entities use this algorithm to cluster the perceived data points. And by integrating all data points from the stream, processing entities can continually update its data and can detect different types of traffic dynamics on themselves. So here our dynamic clustering is based on the mass, and we define two types of agents: data agent and cluster agent. Data agent represents a data point in the stream, contains traffic information and a communicating timestamp. Cluster agents represent an existing cluster representing for traffic dynamic. It contains a centroid and a list of ranges of use. A range of use of a cluster is a time interval indicating the historical moment when the data points have been observed and assigned to this cluster. So by memorizing the centroid and a list of ranges of use, we can keep the information about data points, but we don't need to memorize the data points. So it's convenient, it's suitable to deal with data, the data stream. The diagram here shows the interaction between data agent and cluster agents. The objective of this is to how to integrate the data into the learned database of the processing entity. So first, data agent aims to search the list of existing cluster agents that are similar to the data point contained in it. So data agent sends the request and the data point to all existing cluster agents in the database of processing entity. The cluster agents receive the request. They compute the distance between their centroid to the data point. Then they compare the distance with the local similarity threshold. If this distance is smaller than the local similarity threshold, that means the data point is similar to them. So they send the feedback to the communicating data agent with their identification and the similarity measure. Otherwise, they ignore the request. So thanks to the local learning in Attrib, we can define the definition of similarity measure by considering the characteristic of traffic data we use. For example, if we use the traffic speed or mobility profile of vehicles, we can define different similarity measure. We can also select the value of local similarity threshold by adapting to the characteristic of the processing entities. For example, we can adapt to the length of road segments or the limited speed on the road network we study. So yeah, so that aim to demonstrate the dynamic and open structure of Attrib to adapt to different testing scenario and different combination of data provider and processing entities. So data agent receives the feedback from the existing cluster agents. Here, if they know existing cluster similar to the data point contained in data agent, data agent creates the new cluster for this data point and send this cluster to the learned database. The second case is if there exists more than one cluster similar to the data point. Here we need the cooperation between the existing cluster agents. They need to cooperate between them to decide if they need to merge together. If their centroids are too close to each other, then will be merged together to redefine the position of centroid to adapt to the data point. And after the two previous steps, data agent can be sure that exists at least one existing cluster agent in the database similar to its data. So data agent selects the existing cluster that is the most similar with the data point. And this cluster firstly slightly moves its centroid to the data point using the coefficient, the adjustment coefficient gamma. And it adds the communicating timestamp to the list of ranges of use to update the learning model and the clustering structure. So through the presented learning process, Adrib can succeed integrating new data points and update its database. In fact, Adrib is adequate to deal with the data stream because it has the dynamic structure that can evolve through time to adapt to the new data. And by memorizing the ranges of use and the centroid, we don't need to memorize we can keep only the important information about data. So Adrib doesn't need to keep all the data. And this is efficient because the data stream contains the huge data amount that can arrive continually. So functioning parallelly with the learning process, the prediction process in Adrib performs the calculation of traffic predictions. The objective of this project, process is to estimate the next range of dynamic of traffic dynamics or the next trend of cluster agent. The calculation in Adrib, the prediction calculation in Adrib is updated in real time to adapt to the most recent traffic condition, and also to ensure that the prediction origin is always longer than the required one. So here we developed the cooperative prediction algorithm based on math. We define analyzer agent that is a logical entity to perform the calculation. Analyzer agent use the learned database from the learning process and also cooperate with the neighbors to gather the information, the helpful information for the prediction calculation, because it's based on the hypothesis that is the traffic dynamic on a road segment highly depends on the upstream and downstream. So if we can observe the traffic dynamic on the upstream and downstream, we can improve the prediction calculation. So this cooperation includes the spatial dependency analysis in Adrib via the definition of local traffic configuration. Here, traffic configuration, the local traffic configuration under the point of view of an analyzer agent at timestamp t is the set of traffic dynamics on this analyzer agent and on its neighbors with the corresponding range of use. So the objective of analyzer agent now is to find the historical traffic configuration that is the most similar with the current one. To do this, analyzer agent observes the cluster representing the current traffic dynamic on itself, collect all range of use of this cluster and send them to the neighbors to ask them about their traffic dynamic at the timestamps. After receiving the feedback from the neighbors, analyzer agent constructs at the beginning of every range of use a historical traffic configuration. Now, to compare the historical traffic configuration with the current one, analyzer agent use two criteria. The first one is the number of neighbors giving different traffic dynamic in two configurations. And the second one is the time gap of the propagation time. the propagation time is computed at the time gap between the moment when the analyzer agent and its neighbors change their traffic dynamics. So by evaluating the two criteria, analyzer agent can determine the historical traffic situation in the past, which is most similar with the current observation. So the historical traffic configuration that can minimize both criteria, this is the selected one, and the prediction is defined as the succeeding traffic dynamic observed right after the selected historical traffic configuration, and the predicted changing timestamp when the traffic would be changed. It computed by forwardly moving the current timestamp or time interval equal to the range of use at the selected historical traffic configuration. Analyzer agent repeats this calculation by using the predicted information of previous steps to compute the prediction for the following step until the last predicted changing timestamp is longer than the required one. And in fact, by following this process, we can extend the prediction horizon as long as we want. However, the quality of prediction can be degraded because the accuracy of following step highly depends on the accuracy of previous ones. So if one step gives the wrong prediction, it can impact to the performance of the following steps. But to ensure, so that's why to guarantee the prediction quality of Archive for long term, we propose the self-correction mechanism. The self-correction mechanism is a behavior of analyzer agent. In fact, in Archive, the learning process is continuous. So at every timestamp, analyzer agent can ask the existing cluster agent for the observe the real traffic dynamic. In the other hand, the prediction process can compute the predicted one. So analyzer agent observes both. And if it detects the difference between the prediction and the real observation, they will reload the calculation of prediction using the current observation. So this recalculation can be propagated to the neighbors because the neighbors also use the predicted information of current analyzer agent to view their traffic configuration. But for this point, it also, it can increase the computational cost of Archive. So we will discuss and evaluate this point in the next session. I present the main step of Archive as the generic solution. Now to apply Archive for a concrete scenario, testing scenario, we need to specify the characteristic of data we use in the data agent, the similarity measure and threshold in the cluster agents, the definition of neighborhood of analyzer agents, and the criteria to detect and remove noise in noise detection mechanism. I conducted the experiments applying Archive for two study cases, traffic prediction for microscopic and macroscopic information level. But under the time limit of this defense, I just in the next I will detail the first study case that can directly tackle the traffic congestion anticipation we defined at the beginning. So in this scenario, the set of connected vehicles are playing the role of data provider entities, and the set of road segments from OpenStreetMap are playing the role of processing entities. The connected vehicles collect the data along their itinerary, and at the end of each road segment entity, they send the data collected on this road segment to the associated road segment entity. And road segment entities receive data from all crossing connected vehicles and locally compute the predicted driving behavior on themselves. Here to specify the components I just present, We are interested in the communication timestamp. This is the time interval intra-exist of connected vehicle. And the traffic information we are interested in here, we define the new representation of traffic information. It's named mobility profile. The mobility profile of a vehicle on a road segment is defined as the distribution of travel time for different speed ranges. For example, here, the vehicle moves with the speed at between 0 and 1.5 kilometers per hour during 32 seconds. So the first element of mobility profile is equal to 32 seconds, and so on. The benefits using mobility profile as a traffic dynamic representation, we have two reasons. The first one is we can deduce from the mobility profile, we can deduce several traffic information. For example, the total travel time or the average speed, or also we can observe the variation of vehicle speed on a road segment. The second is mobility profiles is more suitable to deal with data stream processing than the raw time series of speed in terms of the quantity of data we need to be processed. For cluster agents, each of them has a no mobility profile. It is the center of a cluster, the ranges of use, and the similarity measure between two mobility profiles is defined as the vector of difference of travel time for every speed range. So it is the vector of difference. And two mobility profiles are similar to each other if all elements in the vector of difference are smaller than the local similarity threshold. And here we computed the local similarity threshold using the length of road segments and also their limited speed. The analyzer agents define their neighborhood at the direct upstream and downstream road segments to consider the local traffic propagation in the prediction calculation. And lastly, for the noise detection mechanism, here we aim to detect and remove the data from the vehicle in the free flow traffic. So we compute the distance between vehicle to the vehicle in front of them, just in front of them. And if the distance between them is bigger than the stopping side distance, that means these vehicles are in free flow traffic and drivers can drive at their individual behaviors. So that might not correctly reflect on the traffic condition on the road network. So we detect this situation and remove the data. To evaluate adaptive, so I conducted the experiments for both learning and prediction processes. For the learning process, we use data simulated by MOSIM using the very simple road scenario containing two main road segments and one on-ramp road segment. The objective of this simulation is to obtain a dataset containing different traffic dynamics on the two main road segments. So that's why we vary the number of vehicles entering the on-ramp road segment. And here we can choose the different value of alpha, the similarity threshold, 10 seconds for the first row and 5 seconds for the second row, because the first row is double longer than the second one. We compare the performance of dynamic clustering of attribute with clustering using the evaluation metric silhouette. Here, based on the equation of silhouette, the higher value of silhouette stands for the better clustering performance, because we can regroup the data, similar data to the same cluster, and the clusters are well separated. So for the figure here, in both cases, attribute give the higher value of silhouette. That means attribute outperform clustering for the dynamic clustering. We can have the better performance for dynamic clustering compared to clustering. And we can see for some frame, the value of silhouette of attribute can crop. It can be due to the unstable structure, clustering structure of attribute when the new data behaviors arrive, but it can recover in the next frame when attribute successfully adapt its structure to the new data behaviors. For the evaluation of cooperative behaviors of the prediction process, we need to perform attribute in the bigger scenario. So that's why we switch using gamma as simulator to be able to integrate the real row network from OpenStreetMap and simulate data on it. Here we selected the row network at the campus of University of Toulouse 3, Montpellier, where we are deploying the project Neo Campus. The traffic simulated on this scenario expresses different type of variation. For some row segments, we have the very stable traffic, but for the other row segments, the traffic varied beaucoup, so we can obtain the different traffic dynamics. We separate the two groups of row segments, and we will evaluate attribute and the baseline separately on two groups. Here we evaluate prediction using the travel time prediction plan. The travel time is computed from mobility profile at the sum of all elements in the mobility profile. And for two group row segment with low and high traffic variation, attribute without self-correction mechanism gave us the higher prediction errors, so it's not good. So that's why we need the self-correction mechanism to detect and correct the wrong predictions by using the current observation. And attribute with self-correction mechanism in both cases have the better performance compared to the baseline. And this improvement is more significant in case we perform attribute with the row segment with high traffic variation, because in this case traffic varied very strong and irregularly and high with high frequency. So that's why a method including the continuous learning and self-adaptation to adapt to the different type of traffic would be an appropriate solution. And that's why attribute with the self-correction mechanism, self-adaptation mechanism, and continuous learning can perform better in this case compared to the baseline with the static learning process. The self-correction mechanism allowed to improve the prediction accuracy. However, if we use this mechanism with high frequency, that can increase the computational cost of attribute. So now we aim to evaluate the percentages between the number of times we use this mechanism versus the total time we load the prediction of attribute. For all study row segments, we can see that the rates are relatively low, even for the row 46, which is the most used of this mechanism. The rate is only 13%. So that demonstrates the calculation of prediction in attribute is reliable. So that's why it doesn't need to use the self-correction mechanism frequently. To clarify the performance of self-correction mechanism, we select three row segments, 18, 25, and 46, that are the row segment with the minimum average and maximum time we use the self-correction mechanism. And I plotted at every second the difference between the difference of travel time between the observed and predicted mobility profile. Here on the blue line, you can see for 3K, but for 25 and 46, we can see clearer. When analyzer agent can detect the error, it is the big on the blue line. This mechanism can detect this error and correct the wrong prediction immediately. So that's why the errors come back immediately to zero. Another result we aim to study here is the amount of data we need to memorize to perform the prediction calculation. Here I plotted the number of perceived mobility profile versus the number of cluster in attribute for the road segment who has the most data. And even through time, over time, the number of perceived mobility profiles increase, but attribute can keep the stable number of cluster detected. So that demonstrates attribute can efficiently detect all relevant traffic dynamics on this road segment. They can memorize very reasonable amount of data while ensuring the good performance of prediction. So I present attribute and the evaluation of attribute for testing scenario. To conclude, at the beginning, we define 5 components we aim to integrate in attribute to have it having the good performance. And through the design of attribute, we will succeed integrating 5 the elements. Attribute can obtain better predictions in case traffic express the high variation compared to the baseline, thanks to the efficient temporal and spatial analysis. It can also adapt the learning model to the change of environment. Attribute can provide the understanding between of the impacts of traffic factor and road network topology of the predictions. And through 2 study case I conducted, we obtained the same conclusion, the very consistent solution and result obtained by attribute. So attribute can have the strong versatility, model versatility. So besides the advantages of attribute, we determine also the following perspectives to improve its performance from the short term to long term. For short term, we aim to improve the prediction accuracy. We aim to integrate the dynamic clustering method, but for special aspect, we can we can design a dynamic clustering method to regroup the road segments having same characteristic. So that can help in case some road segment lacking the data. And the second is we aim to consider the traffic seasonality in the comparison of configuration that can help to improve the performance of attribute in case some traffic pattern repeated. And the last one is to limit the spread of traffic recalculation. Analyzer agent will observe the recalculation at every prediction steps. And if it detects at some step, the recalculation doesn't change the prediction. So it stops at this step and doesn't propagate the recalculation for next step. For medium term, we aim to apply attribute for the bigger scenario, real world scenario with the diverse type of road segments and different percentage of connected car sharing data to see how attribute perform the prediction in case we lack the data from the connected vehicle. And for long term, at the beginning, we define the multi-level traffic prediction. So we aim to deploy attribute for different level in the road network architecture and see the correlation between the definition, the prediction at the different levels. So the prediction provided by attribute is helpful for we can use the prediction to detect the end of queue, but we didn't deploy attribute for a real world application, the real world end of queue detection. And also collision avoidance system to address directly the traffic congestion challenge. Attribute can also predict the different traffic dynamics, not only the congested traffic. So we can apply attribute for the big recommendation systems, and not only for traffic prediction. Attribute can apply for other prediction problems. For example, currently in our team, we are deploying attribute for the user regularity detection, and this is our current work. So this is my presentation. Thank you for your attention, and now I'm open for the questions from jury and people in the room. Thank you.
Thank you for your presentation. So now that is the moment for the questions. So I propose that the first reviewer starts. So you have the floor, Professor Ha Nhi Ngo.
Okay, thank you very much. Also, thank you for the nice presentation. I also enjoyed reading the PhD. You gently introduce all the concepts that you need. So it's very well done. It's very well structured. So I enjoyed reading your PhD. Obviously, I do have some questions. And a main question I have is, how do you handle noise versus unexpected events? So also in the presentation, you have been talking about noise. I think it was on slide 24, where you explained how to handle noise. But then I'm wondering, yeah, in traffic, you also have unexpected events happening, like an accident, which you do mention in the text. But for me, it's still a bit unclear how you can differentiate these noise versus an unexpected event. So if an accident happens, you have to react on this very fast. So can you explain this a bit to me? So if I'm a user of your system, what should I pay attention to?
Yes, thank you for your question. I had to admit this is about the irregular traffic condition causing by traffic accident or incident. It was a mistake in the thesis. It's the irregular traffic, but it's not a noise. Here with Adgrip, we actually the benefit of Adgrip is the Adgrip can predict the traffic predictions even the irregular traffic situation happen. So if we can consider the traffic incident is the irregular traffic conditions, but they are not the noise in our system. So that's why I removed here I have the new version of thesis, and I remove this line. Indeed, Adgrip can predict traffic predictions even the incident or accident happen. And how to do this? So at the first time the accident or incident happened, Adgrip consider it is a new cluster, new traffic dynamic cluster, and the learning process is a continuous learning process. So it will integrate this new traffic dynamic in the learner database. And at the beginning, Adgrip can provide the wrong decision about this because they don't have enough the historical information about this event to compute the predictions. But when it observe and integrate this situation in the learner database, so if this situation happen again, Adgrip have information to perform it. But at the beginning, yeah, Adgrip can provide the wrong prediction. But we have the self-correction mechanism, and the self-correction mechanism is very efficient in this case because it tracks the prediction quality. So it tracks the prediction and the real traffic dynamic. And if it detects the wrong prediction, it will recompute the prediction using the current observation.
Mm-hmm.
So, yeah.
Okay, so it's a combination of the creating a new cluster and then the self-correction mechanism.
Okay. Yes.
Okay. If I want to use your system, I need to decide on quite a lot of parameters. That's typical in a machine learning approach. So it's not a criticism to what you have been doing, but a problem in general. So if I want to use your system, or there's some guidelines that you can give me on how to set these parameters. I'm especially referring to yeah, the self-learning mechanism, because if I probably set some parameters too high or too low, it becomes a very reactive system compared to a system that needs a quite long time horizon to make predictions. So are you able to advise users of your system on how to set these parameters, how to adjust them so that they fit their use case?
With the self-correction mechanism, yes, it can make the system become very, very reactive. But I mean, like in the prediction process here, I mean, for a trip, we use the predicted information of previous step to compute the next one, so we can extend the traffic origin very long. But if we detect the error, the prediction errors, so we need to come back to the real observation and reload the calculation. This is the same case if we use the traditional prediction method, because the traditional method, we also need to weigh the prediction calculation from the current observation. So so it is the same case for all prediction models. But in a trip, we don't need to recompute, or we don't need to come back to the real observation every time. We can extend the prediction as long as we want with the self-correction mechanism to track and to control the quality. So here for user, you mean like how to choose the parameter to have the good performance is the parameter in a trip. We have the parameter for clustering algorithm. So if we choose the similarity threshold a bit high, the big similarity threshold, so maybe we can obtain a very low number of clusters. And this can cause the underfitting in kind of in the classical machine learning and clustering models. But if we choose the very small similarity threshold, so we can obtain the very, very big the number of clusters. It is overfitting. But in a trip, we can adapt the similarity threshold for different processing entity, different row segment, different, like if we consider the row segment which is very long, or the row segment having the different limited speed, we can adapt the open and adaptive system. So we can adapt the choice of parameter according to the processing entity, to the entities of row network we study. So yeah, is it in the evaluation, to complete the evaluation plan, we need to conduct a test, a test with the different value of parameter. And is the one point in the perspective we need to conduct it for evaluation.
Okay, and would there be a link with, for example, noise level? So could I monitor traffic for a while and maybe look at the noise level to help me decide on those thresholds?
The noise level, because we have the noise detection mechanism. So the parameter here, I don't think it depends on the noise.
I mean, for like deciding on a new cluster.
Sorry.
I mean, and is there a link between the noise level you observe and then setting these thresholds for the clusters?
Yeah, the noise level here is how detailed the number of cluster, you mean, right?
Yeah.
Yeah, definitely, yeah. It's in fact, to in the experiments I conducted, I test with different value of similarity threshold to obtain the reasonable number of cluster of traffic dynamic cluster, because it has a study on the how to define different traffic condition. From which range of big until which range of big we can define, is it the one traffic condition very congested or slightly congested or free flow. Yeah, I based on this study to determine the number of cluster and the similarity threshold. But
Okay.
yeah, maybe it lacks in the thesis.
Yep.
Not mentioned about this test.
Okay, thank you. You mentioned in the thesis and also in the presentation that your method is more interpretable, it's more transparent to the user. Have you done some evaluation, or is this based on feedback you received from users, that your method is more transparent compared to other methods? Can you elaborate a bit on this?
For the real-world application with the user feedback, we didn't conduct this experiment, but through the result we obtained compared to other baseline, we already have the significant improvement, and yeah, in the real-world application with the user feedback, we didn't conduct this experiment.
Okay, so it's based on some some initial feedback you got from the users. Okay.
Yeah.
And then maybe a last question. So at the core of your method is this self-correcting mechanism. Which you now evaluated in a traffic context. Do you think you can use this approach in other use cases as well, in other domains? Because it's a quite general concept that you now introduced. So do you see potential for other application domains with this method, with these ideas?
Yes. Currently in our teams in Toulouse, we are applying it's not applying attribute, but use the main concept of attribute to detect the user regularity. If the user like for the trajectory of user, they go to work by bus with different type of transportation mode. So if they used to work by bus and go to the shopping by car, for example, is it the user trajectory? And we use the concept of attribute to detect user regularity and provide some recommendation. For example, today have some problem with the public transportation, so we can give some recommendation for this user to train the mode of transportation. And also attribute is it the current work, but we also can apply attribute for the prediction problems if they have the different entities interact, and if this problem have different entity interactive entity, the local learning allow us to learn locally, so that allow to reduce the calculation time, the data, and also that can like address the data privacy problem. So, and the cooperation between entity can share the data or just share the output of learning process. So yeah, it can help to keep the data privacy. So yeah, attribute can apply for this kind of prediction problem where we have different entity and we need to keep the data privacy within entities. Yeah.
Okay, thank you very much for your answers to my questions. I'll give the
Thank you for your questions.
back to the chairman of the defense.
Thank you very much for your questions. So now I will have the role of reviewer.
Yes.
My question will be very close of the one of my colleagues. But at first, I want to thank the supervisors of your PhD for the invitation to review your document. Thank you. It was a pleasure because you make efforts to produce a document with some pedagogical objective. Even if sometimes there are parts of your document where that is difficult to understand some elements that because they are presented after. That was one of my remarks in my report. But in general, it was all very clear, and your presentation is clear also. So thank you very much for this. I have another remark about your works and in your documents that is a number of references of the state of the art is very important. And in addition, you propose some syntheses with comparison of subset of these works, it depends on the part. Yeah. And what is interesting is that it goes beyond only a discussion about this work, because we have a comparison, we can agree or not, but we have a comparison and can discuss about it. That is very interesting. So thank you for this document one more time. So now I have some questions. I have some questions that are details about your work, and after I will have some more general questions. My first question that is very detailed, but it was clear for me, and you don't use it in your example. Why we will have several entities for network? What you have in mind is?
You mean the road network entities or the
network entities at the top of your hierarchy?
Yep.
In fact, I have two questions. Why you need a fund? You want to have several entities, one by type of network, and what you call type of network in that case. And from my point of view, your work is more at a microscopic level. Yeah. So how you consider this work at the level of a complete network?
The first question is about why we define several entities in the road network. Here we aim to develop Active as a generic solution for traffic prediction problems. In the experiments, I conducted two cases with the microscopic, it is the case I presented, and the macroscopic is the case with the real world data. And because the Active, we aim to have the prediction with different level. The prediction can use for different purpose. For example, for the microscopic level, it's very helpful to provide the microscopic prediction for driver for the connected vehicles. So this is our case. But also for the macroscopic, the prediction can help for traffic management. For example, at the level of city or a district, for example. If we for traffic management, if we detect that the traffic congestion happen at some region or some area, it helps improve traffic management, and also to, like, for example, to help driver to choose another itinerary to avoid the traffic collision. So the objective here with the different level of traffic is to obtain traffic prediction at different level for different use case.
Okay, thank you. I have another question about one more time that is detailed. Yeah. In your document, there is a part related to self-organization, and in this, you write that you consider that the entity may want to put themselves on standby to give priority to other entities. And you have some kind of sentence where we can see some organization some coordination between agents. But in fact, in your presentation, in your document, it was not so clear. So where are these mechanisms? Because, for instance, you want that some agents can wait the answer of the others and so on. How really that is done, in fact? Because we have not. Your document is really more focused on the transportation problem, the prediction problem. So that is clear. But the behavior of the multi-agent system behind is not so clear for me.
Yeah. So the analyzer agent, they cooperate together. So in the cooperation, they have the here what I presented is the cooperative behavior. That the behavior when the cooperation happens smoothly. However, but for example, in the case you mentioned is the first case of non-cooperative behavior. For example, here, because analyzer agent used the predicted information of previous step to compute the next one. So, for example, here at this step, it needs to ask the neighbors for the information, the predicted information at this timestamp. But in case the neighbors, the neighboring analyzer agent, they haven't computed the prediction yet at this timestamp yet, so they cannot send the information to the demanding analyzer agent. In this case, it's a non-cooperation case because the cooperation doesn't go smoothly. And in this case, it's the self-organization in attribute based on AMAS. The rule here is the analyzer agent having the shortest prediction origin who loads the calculation first, and the other need to wait because if they ask the information from this analyzer agent, it's
just to understand.
Yeah.
When you say that the agent which has the shortest prediction horizon, how he knows that he has the shortest horizon?
Because the system doesn't know which one is to have the shortest one. But the analyzer agent, when they require, they ask the data and they didn't receive the feedback. So the behavior here is need to wait because the neighbors may have the shorter prediction horizon. So it doesn't, the system don't know which one is shortest one. Yeah.
Okay.
But, yeah.
That is a result of the what you write, that is a result of the interaction, in fact, but that is not encoded into the system.
Yeah.
Okay, thank you. I have another question, but in fact, the use of the system itself. As I said, from my point of view, it seems to be very efficient at a micro level. At a micro level, the objective is to inform the drivers that there is a problem, some kind of problem, in order that he change his own behavior.
Yeah.
In that case, it means that you will change, in fact, the future, because the driver will adapt his own behavior, and so the prediction will be false.
Yeah.
So how you consider this that is not detailed, it seems, in your example, that is not taken into account in your example, and how you think it will influence your proposal?
Yes, because in my knowledge, when I read the state of the art of traffic prediction, is more the research about the macroscopic level than the microscopic level, because the macroscopic level is used for traffic planification and the management. So we know about the future. We supposed to know about the future, but we want to change the strategy, not change the future. But at the microscopic level, at my knowledge, when I read state of the art, at the microscopic traffic prediction can help to to compute the battery remaining in the electric vehicle. It's not to train the the route. So yes, when we know about we compute the predictions, we inform driver the future traffic. So driver might train their itinerary. So that's why we could train maybe the road we predict before it's the traffic congestion happen. But if many driver train, so this road become less congested and not the road become like more congested. And this is that's why it's important to have the continuous learning to observe the real condition of traffic and with self-correction it's important to observe the new traffic and include in the learning model. Is it the benefit of continuous learning?
I understand this point, but my question was not that it was my question, but it was more about the specific case. That is your first example where we have a road with another road that enter in this. And in fact, you have no modification of the route of the users or the drivers, but you will have some modification of their behavior on this road. And the objective of your system is you anticipate the future state of this road.
Yes.
But what is not clear for me is if the driver who is informed of there is a problem on this road, but he has to go in this route. It was your example. And in that case, he will change his behavior, he will brake, for instance. It means that it will become a noise in the system. The system will configure will just modify the configuration to have the current state of the system. How do you think your system will adapt itself to the modification of the system?
The modification of traffic condition. Not
exactly. Yeah, you anticipate that we will have a traffic jam on the road.
Yes.
So a new driver arrives.
Yes.
So we anticipate that the traffic jam will increase because we have new drivers. But these drivers are informed, so they change their behavior. They brake, for instance.
Yes.
We can imagine that we will have how to say. Even in French. Ouais.
Oui.
Même en français, en fait. C'est pour ça que ça vient pas. Ça devient plus compliqué. On va voir, en fait, we will have some regularities in the speed of the driver. So we will have something that will not be at the end a real traffic jam, but something with a lot of vehicles, but we can drive. Okay, yes. So that is not the situation that was anticipated.
Yes.
How your system will react. That is.
In this case, the predicted traffic dynamics is different with the current one because driver train the behavior. So it's the main key of self-correction mechanism. Maybe we can don't have enough time to provide the current one. It's not the prediction, it's the current observation. But in this system, you see, we can detect the change of traffic. We detect that our prediction doesn't good because the driver can change. But we are able to know about this. We observe from the continuous learning, and we can inform this observation to drivers. Maybe it's don't have the long enough reaction time, but is it I mean, we can detect it and we can update it. It's even more efficient than the learning model. It's static one. You don't learn from the current observation. It's just based on the the trained model. Maybe in this case, they cannot detect this trend, and the driver always like have the very old prediction, very I mean, in this case, driver can get mad because they have the real observation. It's very different with the prediction, but the system doesn't say anything. It's still like prediction, even the prediction not good.
Okay. So I had question as my colleague about noise. No, I had question about noise detection, but you answer. I have a question about parameters too, but you answer to a part.
I can hear you very well. It's good. Yes. It's cool.
You explain that, for instance, you have parameter like lambda or alpha and so on, and you explain that this parameter depends on the length of the road, for instance. I don't remember exactly, and finally, you answer, if my understanding is correct, you answer that their value depends of test. So there is some kind of calibration of your model. And how you know that these are the good parameters? That is one part of the question. And the other part is perhaps, if that is not true, that is a perspective question. So you can imagine that you could adapt these parameters during the running of the system according to for instance, the number of times that you have to reconfigure to reset to the current state of the system.
Yeah, we have several parameters. We need to define at the beginning of system. For example, the similarity threshold to detect the different, to distinguish the different traffic conditions. And they see we have a study about this to detect which kind of like the gap in the traffic speed. Like for example, which range of speed we can define as it a type of traffic condition. So we can base on this research to choose this parameter. But also it depends on the characteristic of road segment. For example, if a road segment is a long one, we need to the vehicles need like more time to cross this road segment. So we need to choose the parameter, the similarity in the mobility profile would be bigger, because if we choose the same similarity threshold for all road segment, for example, the short one with the bigger one. So for some road segment, we can detect only one cluster because the similarity threshold is so big. And for the long road segment, we detect a lot of cluster because the similarity is too small. So it's the benefit of local learning. So we can distributed learning. We can choose different value of parameter for different entities. And in the question about the reaction time, how long we set up to reduce the current observation, for example. Here is for now in my experiment, whenever the analyzer agent detect error, we will come back to the current observation. And yeah, if in the case if the traffic change very with the strong traffic variation, we can like come back very frequently. But I mean, it's the same case as I mentioned in the answer for An. Even for the classical prediction method, they use the current observation to compute the prediction until the 5 minutes or 5 minutes later, for example. So vehicle always need to wait from the current observation, wait the prediction calculation time to obtain the prediction. But us, we don't need to come back every time. We extend prediction. We only need to come back when we detect error. So we don't have a time set up for the how long or until when we come back to the current. whenever the analyzer agent detects error, we will come back to the current and reload the calculation. But we also have the perspective. We can limit the propagation of recalculation. We can observe at, for example, the prediction can change for previous step, but for some next step, maybe the recalculation doesn't change the prediction. So we stop at this step.
Okay, but do you think that you could modify these values dynamically according to the evolution of the, because if we imagine that your system is deployed, the network change in time.
Yeah.
So perhaps the values that was computed at the beginning of the system are not adapted.
Yes, we can change the parameter, you mean.
Yes, exactly. And you could do that without observation of the system and to see if you need to recalibrate dynamically your parameters. Okay.
Yeah, because it's a system, I believe it's open. So, for example, the benefit using AMAS, the local learning and cooperative prediction is because in row segment, maybe we have some row will close for the working reason, or they will open new row segment, for example. So the change of the row segment doesn't disturb or interrupt the function of active. We don't need to reload or retraining the prediction model as the classical one. We just remove the agent and add some agent if necessary.
Thank you very much for your question. So I propose to refer to Mr. I don't remember. No, not your name. Examiner with Cooperative.
Thank you very much. Thank you very much for a very clear presentation, and thank you to your supervisors for inviting me to be part of this committee. I very much enjoyed reading your thesis, and I very much enjoyed your presentation. It was very pedagogical, very clearly set up. You've had a fair number of questions already, but I can't help myself. And I will ask a couple of detailed questions, and then I will ask a couple of questions which are beyond the scope of your thesis to assess your, because, you know, I'll get to them. I have one detailed question. Could you bring up the slide with the mobility profile, the MP?
The mobility profile?
Yeah.
Yes. It's gonna be here.
Yeah, that one. I quite like the idea. In general, in multi-agent systems, choosing the right agents, but also choosing, in this case, choosing the right data to feed them with, or the right signature. I guess you could call this a signature of a data point, right?
Yeah.
And I quite like it. I did have a thought though, like if you have a segment and you have one observation of a vehicle coming in at 50 kilometers an hour and like perfectly linearly descending to zero at the end, and you have another vehicle coming in that starts at zero and perfectly linearly accelerates to 50 kilometers per hour, would you have the same MP for those two observations?
In two cases, we will have the same mobility profile.
Yeah, that's what I thought. But what do you think? In which case do you think this could cause a problem?
Yes, because the objective here is we aim to predict the position of the end of jump Q.
Yeah.
So in the row segment, if we have at the beginning, the vehicle can arrive very with high speed, and at the end, the speed drop.
Yeah.
And the second case, the traffic congestion happen at the beginning of row segment. So yeah, in two cases we have the same mobility profile. So, but in the here's it just like the local observation. We can, if we extend the observation, it's the upstream and downstream row segments, for example. We can observe also because we predict like the road segment in the road network can predict the behavior. So, for example, the can say the upstream road segment can give you the mobility profile with the very many time of with the how do you say the measure travel time vehicle drive with the low speed and the current road segment. We also observe this, but the next one we see that the traffic light is less congested. So we can observe the sequence of mobility profile from the sequence of road segment. So maybe in this case, the traffic congestion happen at the beginning of the current segment and at the end of the previous one. So we observe not only locally the mobility profile on one road segment, but we observe the sequence of mobility profile on the sequence of road segments. And maybe we can here I choose the road segment depend by the OpenStreetMap. So it's the road segment divided by the road between two intersections. But if we want to have the more detailed information from the traffic, we can define the road segment by themselves with the length we decided, with the level of regularity. You can say the noise or the detail of prediction that we want. So we can define the road segment by ourselves.
Very good answer. That was it. That answered my next question as well.
Thank you.
Very good. Yeah. Since we're still there, I still cannot help myself. This is still a detailed question. But if you have like from OpenStreetMap, for instance, you can have very short sections. You can have extremely long sections. It just depends on whoever coded that part of it. How would that impact? I know you do some filtering and some concatenation, but if you wouldn't, how would that impact? What would that cause for problems for your system? If you would have very short sections, very long sections.
Yeah, with the long section, that's why we choose we compute the similarity threshold depend on the length of road segment. Like when I select the road network in the campus of university, we have many very short road segments, and because we based on the similarity different in the time travel to detect different cluster. But with the short road segment, even we decrease the similarity threshold, we only detect only one cluster, and it impact on the performance of attribute for prediction, because the neighbor of this road segment can have only like always the same feedback from the same traffic dynamic to build the traffic configuration. So basically, this road segment doesn't play any role for the prediction of the current one, the neighbors. So yeah, for the long road segment, we compute basically we can choose a different similarity threshold for
This is a well-known problem also in traffic modeling. If you have a very short segment, you have jam density if there's a vehicle, or you have free flow when there's no vehicle.
Yeah,
and it becomes a binary function.
Yes.
So this is what's driving probably your observation as well. Very good. I have one more detailed question, and then we go to the more general questions. One more detailed question, which is, I think Flavien was touching on it as well. How sensitive is your model to choosing the wrong parameters? Say, you show that, like the number of clusters remains reasonable even with larger instances. But what if they wouldn't? Say, what if you would have 5 instead of 15, or 3 clusters, or what if you would have 50 clusters? How sensitive is the system to getting it right?
Yeah, it's to complete the evaluation plan, we need to conduct the sensitivity test for like how the performance of attribute depends on the choice of a parameter. Here I didn't detail in the thesis and the presentation also, but when I select the similarity threshold, I did this test. I did this test by myself, but I didn't present in the thesis. I did this test to see the number of cluster, how it varies based on the selection of the value of similarity threshold, and I select this parameter, the similarity threshold. When I see the number of cluster, we can say reasonable, but we cannot have like 100 or 50 cluster for different traffic dynamics, because traffic dynamic we have basically 5 or 6. It's less than 10. So I with the equation to compute similarity threshold, I choose some parameter and I observe how many cluster it the attribute give, and I select the reasonable number, because for now I didn't find the study to say like which number of cluster is good and which one. So that's why it's just a
there was fought over this.
So it is a test need to include in the evaluation.
I think it's a good answer. It is difficult. It is an important part. This brings me to my next more general question. Say Continental would like to develop this into a product, right? It is okay. Well, excellent, really, really nice. What are, if you give them, it's okay, these are my recommendations. What are the necessary next steps for them to do in order, like before this could be, implemented into a product? So what would be the next steps for them to do?
Yes. The precision barrier we can use to, as I explained, we can use to detect the end of jump queue. It is the objective, because we built the thesis based on the challenge we found at Continental, and we aim to detect the evolution, also the position, but the evolution of the end of jump queue. So I mean, for the elements we mix, the first one is about the data, because we need the data from the connected vehicle on the road network to see, but of course we won't have the data from all connected vehicles. That's why in the perspective I mentioned about we need to vary how the percentage of connected vehicle sharing data we need to perform the good predictions. This is the first element about the data collected. We need to have enough amount of connected vehicle sharing data. The second is about because at RIP we aim to embed at RIP in the embedded device. We provide the prediction, but we let drivers make decision about this. So I mean, for the second step, I mean, it's about about the prediction error also. Like we show that we can improve the prediction compared to baseline, but if like 15 seconds of prediction error is enough in case of real world application or not. If acceptable for continuous or autonomous vehicle.
So you should test that as well, yeah.
Yes, and we discussed with people at Continental, and so for example, on the long segment, 50 or 15 seconds is acceptable, but with a short one, no, it's not, because short one we need only take, for example, 10 seconds to cross the segment. So 15-second error is not good. But in the calculation of my experiment, we have the average for all segments. So yeah, we need to evaluate adapting to the segment and to see what range of error is acceptable for connected and autonomous vehicle.
Excellent, thank you. I think that finishes my questions.
Thank you for your questions.
Thank you very much. So now we will give the floor to your supervisors. I propose to start from the left to the right. So at first we will have the question, comments of Anaïs Courzel.
Thank you, Ali, for the work you did with us on this topic. It was very interesting to work on it. I have only one question. So you did a case study in collaboration with KTH.
Yeah.
Can you explain what are your conclusions and challenges on using real world data? And I think it's related with your previous question, Wilco.
Yeah, because to validate the system, for the microscopic, because we don't have enough data from connected vehicles, so we need to perform active using simulated data. But to validate the system, we need to perform in the real world data, and that's it. That's what my 3 months visit at the team of Wilco here in KTH in Stockholm. And in this application, in this study case, we use data collected from the sensor, the fixed sensor. They collect the data in higher level. The sensor collects data. Is the aggregated data is the number of the average vehicle speed and the density, how many vehicle cross during a time interval. The time interval is, if I remember well, it's 15 minutes. Every 15 minutes we have one data. So this data is a higher level, and because it is the aggregated data, so the variation of data is less than the microscopic level. And with the data with less variation, the traditional method can work pretty well. It's we design at its microscopic level with the high variation that I showed with the low with high traffic variation. It's work like better than the other, but with the data with less variation, I prepared some slide for this application. Here. So even for the high traffic variation at with the first the mean average error at give us the higher level compared higher error compared to the STM and GRU. But in the second criteria, we obtain the best performance with the lowest error. So here we aim to adapt to a trip with different level, but with the level with less variation, we have the very how to say the concurrence with the existing method. So that's why I think for one point in the perspective, for example, we aim to include the traffic seasonality in the comparison of traffic to detect the case in the traffic pattern repeat. So that case we expect improving at trip in the case with less variation. It's kind of like we have the very regular traffic, but is it a trade-off? We aim to is it a trade-off if we the way we include this property in the comparison? Because if we just focus 100% in the traffic seasonality, so we will reduce the dynamic property of at-trip. So yeah, so it's a perspective, but to deploy it, it's a lot of study behind, because how to keep the dynamic property of at-trip for the high variation case, but also include the traffic seasonality to detect the traffic pattern, because this case is very easy to, it's easier to predict than the dynamic. So yeah.
Thank you very much, Ha Nhi. It was a very clear presentation, so thank you very much for the presentation and for the three years you did in Continental.
4 years.
4 years, yes, indeed.
1 year of apprenticeship.
Yeah. What very good evolution since you come at intern beginning at Continental. So thank you very much, and thank you very much to Elsie, Marie-Pierre, and the SMAC team for this collaboration. The first, maybe the future one, I hope so. It was very a pleasure for me to come back after my PhD with you. Yes, and as you state, this subject is very important for us because we cannot only rely on car sensor, and we have more and more data, so we need good application to deal with this high complexity problem. So this study, this PhD was very interesting for us, and I think it's a beginning of something at Continental, because we have more and more question of our customer about detecting and managing end of queue, as you state. So yeah, I think with your many contribution, we will be able to do something, and I hope so. So thank you very much for all your work you did, Hani. Very interesting work. And I have a little question, of course, because it's mandatory. So in the last part of your thesis, you state that one opportunity could be to deal with human itinerary, something like that.
Yeah.
So did you start to do something, or this is just a project you have to adapt ADRIP to this topic?
Is it a project for user for user regularity detection? We published an article, paper, scientific paper. Firstly, we for that paper, we use the concept of the processing of the learning process in ADRIP to detect different user itinerary. And yeah, it's the current work. So we published one article, and we are working for the prediction process for this. Yeah.
Thank you very much, Jenny.
Thank you. So now we'll have the question, remarks by Elsie Kadum, who is the co-director of the PhD.
Thank you, Flavia. I don't have any question, Hani. I think that you had a lot of discussion together. Well, I would like first to thank all the jury's members for being here today, Anne and Flavia, for your valuable report, remarks, and questions. We'll go first for welcoming Hani with Eric and Mate for 3 months at the KTH Royal Institute. I think it was a very important human and scientific experience for Hani. Thank you all also for the very interesting discussion we're having yesterday and your question today. Jonathan and Anaïs, thank you for the interesting subject. You are now living with a lot of perspectives, so hope to pursue this collaboration in the near future. Marie-Pierre, thank you for your trust to enable me to co-direct this thesis with you. It was, and it is, a great pleasure to collaborate with you, Hani, because yes, it was a more collaboration than a supervision. I remember the first meeting we had, I was saying to myself, well, the discussion will be difficult. But at the end, it wasn't. And why? Because, Hani, you are a very hard worker, a determined person, and whenever you encounter any difficulty, you take the time to work on it. When you have a remark on your work, you find the right answers and arguments, either to improve it or defend it. You worked on your language difficulty, and yeah, today we can see the progress you have done. You took lessons on time series, machine learning, neural network, reinforcement learning, to be able to understand them, explain them to us in an educational and pedagogical way, and implement those different techniques to compare and validate your system. All your meetings were very well prepared. You had the results, their analysis, and the different directions that might be taken to improve your system and go beyond. So to conclude, you're not coming to pursue in the academic field, but I'm sure that we'll continue collaborating, and I just want to wish you the best for your future. Thank you.
Thank you, Nancy. Thank you very much.
Thank you very much. So now we will have the question, remarks
Oh, no
by
question.
your director.
I have no question. Thank you, President. So to complete the question about real experiment, we are now we are trying to develop a platform of experiment in the on our campus. And I hope so soon we will have several vehicles we can move on the campus, and why not try to simulate and then to do this in a real world, but not during the ANI thesis because we are at the beginning. So it was. I am very proud of the work done, and to see that AMS are still used to solve complex problem and dynamic problem. I think that this theory, it's very important because the problem of we have to solve become more and more complex and dynamic. Is I think it's a future, always a future. So it's very important for the team you have done. So first of all, I would like to thank Anne and Flavia for the report on the thesis. It's always a big work to do because we have to read and to understand a new work. And thank you for this work. Then thank you, Wilco, to be here today and to have welcomed Annie and Elsie in Sweden during sometimes 3 months for Annie. Elsie, I don't remember. 15 days? Okay. And I hope that the cooperation will continue now between your team and our team. I'd like to thank a lot Elsie because she acts as day-to-day supervisor for this PhD because I wasn't always there because I have a lot of responsibilities. And I think that you follow Annie very closely and provide your expertise to Annie. You can be very proud of the results, I think. And I hope that you will soon defend your HDR. You prove that you can. So it will be a great pleasure to be in your jury to do that. Annie, I congratulate you for your work. Big work. It was not again at the beginning. It was a very complex problem. So I congratulate you for this work, for the presentation also. As Elsie said, you have do a lot of progress in language, English and French. At the beginning, we have some problem to understand each other with the accent, but it was now very nice. I thank you for all your years in the SMAC team. You are a PhD student that every thesis director wants to have, I think. You are very competent on on computer science, of course, on mathematics, on presentation. So you have a lot of skills, very important skills. You are very serious and diligent, hardworking, as said Elsie. You never stop and say, okay, I will arrive, and you work. You are pugnacious. It's a very important quality in the life for research and other. What is important for us that you take into account the advice of your supervisor every time you propose, but also you know to follow advices. And it's important to work in a group and in a team. I think that you are also a beautiful person. Yes, very sociable. And you are also expert in making names and spring rolls, which is a big quality to be in a very friendly team and social team. So for all of this, thank you very much, Annie. And I wish you the best for your future work and hope that not with me because soon I will be in retreat, but with Elsie and the SMAC team, you have a collaboration. And I hope we will continue collaboration with Continental. We have yet another PhD, but why not others? Thank you.
Thank you, Marie-Pierre.
Avant tout, est-ce qu'il y aurait des questions dans l'audience de docteur? Yes, oui.
Yes, thanks for the presentation. I just wanted to understand better how the self-correcting part works.
Yes. Okay. The self-correction mechanism is the behavior of analyzer agent. Analyzer agent is the logical to compute that performs the prediction calculation. And here, the analyzer agent use the predicted information of previous step to compute the next one. So the performance can be degraded. And how it works? Here, analyzer agent can ask the cluster agent for the observed traffic dynamic at every timestamp because we have the continuous learning. And at the other hand, it computes by itself the predicted. So basically, the principle of self-correction mechanism is compare the prediction and the real one. But it can happen because we have the continuous learning, and we can observe at every timestamp a real traffic dynamic, and we integrate the real traffic dynamic in the learning process. So the principle here is the analyzer agent observe to the prediction and the real observation and compare it. If they detect the error, they will reload it, because here to compute the prediction, the analyzer agent use the predicted information. It's not the current, it's not the real observation. Then the self-correction mechanism will make the system come back to the real observation to reload the calculation for the next step. I hope it's clear.
Thank you. Other questions? Non. OK. Donc, le jury va les délibérer. On reste dans cette salle, donc ça veut dire qu'il faut libérer la salle. Merci. Ça, par contre.